Hello, welcome to Learning Chemistry with Reba. Today we will discuss one of the most important and famous pericyclic reaction, Diels-Alder reaction, which was first reported by these two scientists, Otto Diel and his student Kurt Alder in 1928, and later in 1950 they received a Nobel Prize for this reaction. And this is the general schematic representation for the Diels-Alder reaction. Before moving into the further explanation of pericyclic reaction, we should know what is the difference between a pericyclic reaction from other organic reaction. Almost all organic reactions other than the pericyclic reaction, they involve some reactive intermediate in its mechanisms. All the reactions, organic reaction, have a multi-step reaction mechanism, and those mechanisms involve some reactive intermediates. It can be carbocation or carbanion or free radical or carbene or nitrene or benzene, likewise. Here we can see one example for those organic reaction, that is lactone formation from beta hydroxycarboxylic acid, which is an acid catalyzed reaction, and we can see here a carbocation is formed in this reaction. That means without this formation of this carbocation, this lactone formation could not take place. So, almost all organic reaction may involve any one of the reactive intermediate, maybe carbocation or carbanion or free radical or any other reactive intermediate. So, the primary difference with the pericyclic reaction is that it involves a reactive intermediate with multi-step mechanisms. When it comes to the pericyclic reaction, unlike the other organic reactions, this pericyclic reaction do not involve any reactive intermediate. The pericyclic reactions do not involve any reactive intermediate like carbocation or carbanion, and also it proceeds via a single step or mechanism only. It do not involve any multi-step, just it proceeds via a single step mechanism only. Here it is shown an example with the Diels-Alder reaction. And here we can see a single step leads to the product. So a pericycle, the main basic point is that do not involve in a reactive intermediate, and then it proceeds via a single step mechanism. Pericyclic reaction can be categorized into electrocyclic reaction, sigmatropic rearrangement, cycloaddition. Since we are dealing with this Diels-Alder reaction, we are now focusing only on the cycloaddition reaction. Later in some videos we can discuss what are electrocyclic reactions, what are sigmatropic rearrangements and other pericyclic reactions. Here in cycloaddition reaction, we can see it is the just cyclic addition of the reactant. The reactant adds to get a cyclic product here. Here we can see a butadiene adds to ethene to get a cyclohexane. It's a cyclic addition of the reactant in a single step to get a cyclic product without any formation of reactive intermediate. So here we can see it is denoted like as Diels-Alder reaction is denoted like 4+2 cycloaddition, which means one of the reactant have 4 carbon atoms which is directly involved in the reaction, and the other reactant has 2 carbon atoms directly involved in reaction. So in general, cycloaddition reactions are categorized in terms of the number of carbon atoms involved in the reaction. Here, since it is one reactant include 4 and the other has 2, then it is a 4+2. So these are a reaction are always 4+2 cycloaddition reaction. Apart from this, there are different cycloaddition reaction, 2+2, 3+4, like cycloaddition reactions are involved. We can see later in different videos regarding cycloaddition reactions. So here also we can see that here there are in part of the reactant there are 3 pi bonds, but when it comes to the product we can see only 1 pi bond. That means 2 pi bonds have disappeared, whereas 2 new sigma bonds have appeared. So in a 4+2 cycloaddition Diels-Alder reaction, Here, two pi bonds disappears and two sigma bonds appears. The other point for the pericyclic reaction is there occurs a simultaneous bond formation of these two sigma bonds and simultaneous bond breaking of two pi bonds. That means the pi bond disappearance and the sigma bond appearance are occurring in a single step. That means simultaneously the both phenomenon occur. That is one of the specific characteristic feature of this pericyclic reaction, cycloaddition reaction. That means here we can see the simultaneous disappearance of two pi bonds and appearance of two sigma bonds. Also, we can say, though there is no formation of reactant intermediate, in pericyclic reactions, we can see the formation of some transition state during the reaction. The transition state is not a reactant intermediate. Transition state is high energy species. So it's just a transition from reactant to product. Here we can see a butadiene reacting with the malic anhydrine, and we can see this is a 4 plus 2 cycloaddition. The reactant, one of the reactant butadiene has 4 centers, carbon centers, and here it has only 2. And this is a 4 plus 2 cycloaddition. And in the transition state, we can see since the bond forming and bond breaking is a simultaneous process, this is denoted like a dotted line, which means here the bond breaking, the pi bond breaking and the pi bond formation and the sigma bond formation is occurring are occurring simultaneously. And what is this? And that is what shown in this image, which means this is the transition state between the reaction and the product. This is a 6-member transition state, which moreover resembles the structure of a benzene with a 6 delocalized pi electron. We can see that 6 pi electrons are involving in this transition state, which adds up to the stability of this pericyclic reaction. And a 6-member cyclic transition state then later leads to this product involving a cyclohexane in the product, which means a pericyclic reaction always involves a transition state. It do not involve reactant intermediate, but it has a transition state. This 4 plus 2 cycloaddition reaction has a 6-member transition state leading to the product. And this is the orbital diagram showing the interaction of the reactant during the Diels-Alder reaction. Here it is shown the orbital diagram for the diene, and here it is shown the orbital diagram for the malic anhydride, and we can see a new pi bond is formed and two new sigma bonds are formed between these two reactants. Here we can see the two reactants are connected by using the sigma bonds, and the same way here we can see the suprafacial interaction of the two reactants to get a new sigma bond. This orbital explanation will be given in the next video. Here we can, in short, we can see here an interaction, a suprafacial interaction, and we can see it in detail in the next video. On moving to the further detail of Diels-Alder reaction, we can say that Diels-Alder reaction is a thermal catalyzed cycloaddition reaction. That means without the aid of thermal condition, this reaction could not take place. It's a reaction between a conjugated diene and a dienophile. Dienophile could be alkene or alkyne compound. Here we can see some diene. This is a cyclobutadiene and this is a cyclopentadiene. Here we can see these two are conjugated diene. That means alternate double and single bonds are present, and so the one component for the Diels-Alder reaction is diene and the second component for the Diels-Alder reaction is a dienophile, which could be alkene component or alkyne component. Here it is ethene, this is malic anhydride, and this is ethine, and this is benzene. So a Diels-Alder reaction is a reaction between, is a thermal reaction, catalyzed reaction between a diene and a dienophile. And also this is a 4 plus 2 cycloaddition reaction. Here we can see some examples for the Diels-Alder reaction. The first example shows the reaction between buta-1,3-diene and ethene, which is thermally catalyzed to get cyclohexene. Next, we have changed the dienophile. These all are dienophiles. We have changed it to prop-1-ene the same diene, buta-1,3-diene, which is thermally catalyzed to get this product, and we have then changed the diene to isoprene, which is the monomer for the natural rubble with a reaction with the maleic anhydride or furan 2,5 dione, thermally catalyzed to get this product. Here all we can see that this is a 4+2 cycloaddition, 4 carbon atoms from the part of diene and 2 carbon atoms from the part of diene. Fine. These are the general introduction or the general definition for the Diels-Alder reaction. Further detail of the characteristic features of a diene to be a part of a Diels-Alder reaction, we have to say first point is that it can be cyclic or acyclic. We can take a cyclic diene or acyclic diene. We can take butadiene or cyclopentadiene. And then the second most important point is the diene should be electron rich. The double bond of the diene should be electron rich. The electron density in the diene should be more. And the third point for the diene is it should be of S-cis conformation, which means the S of this conformation denotes the sigma bond, and we can see what's the difference between the S trans and S-cis conformation. S trans means with respect to the sigma bond between the two double bonds, the two double bonds should be trans to each other. With respect to the sigma bond, the double bond should be trans to each other for the S trans conformation, and if the double bond is cis to each other with respect to this double bond, that is S-cis conformation. So these two, since both are conformations, they can easily interchange with each other with a more stable configuration of S trans. So the equilibrium is more towards the left here. And so, when it comes to the Diels-Alder reaction, the diene should be of S-cis conformation. So these are the three characteristic points or features that a diene should possess to take part in the Diels-Alder reaction. Here are some examples for the S-cis conformed dienes and S-trans conformed dienes. Here we can see that this is a cyclopentadiene, and we can see with respect to this sigma bond, these two double bonds are cis, and this is another example for the S-cis diene furan, and this is another example. Here also we can see that this has a cis conformation, and here also cyclohexadiene. Here also we can see a cis conformation. And when it comes to these two examples, we can see a S-trans conformation because the double bond configuration with respect to this sigma bond is trans to each other. So this is an S-trans conformation, and here also these two double bonds with respect to this single bond is trans to each other, and this is also S-trans conformation. So if the diene is the S-trans conformation before the reaction, if it is capable to come to the S-cis conformation, then the reaction could proceed. But if the diene is not possible to convert to the S-cis conformation, then the reaction will not proceed with S-trans conformation. Look here, this is S-trans conformation, but it can never be converted to the S-cis conformation. This is because this structure is a cyclic structure, and hence it could not be transformed into the S-cis conformation. So these two reactants cannot take part in Diels-Alder reaction. But when it comes to the butadiene, even though the butadiene, the most stable structure is S-trans, but when it comes for the Diels-Alder reaction, it could be transformed into the S-cis conformation with the low energy barrier. Mostly, the S-trans conformation can be converted to S-cis conformation only for the acyclic dienes. For the cyclic dienes, it is difficult and it is not possible to convert S-trans to S-cis conformation, and for the cyclic S-trans conformed diene, conjugated diene cannot take part in the Diels-Alder reaction. And we have said that the diene should be electron rich. That means the double bond should be electron rich. To make diene more electron rich, we can substitute the diene with some electron releasing groups or electron donating group. Here we can see we have introduced some electron donating group, alkyl group, here methyl group. And if we introduce some alkyl groups to the double bond, we can increase the electron density at the double bond, thereby the reactivity of the diene for the Diels-Alder reaction. Also, the configuration also plays some roles for the diene reactivity. Here we can see that this is a simple diene with no substitution, but this is a diene with a substitution of methyl group, but this diene is S diene. That means S alkene. Here the alkene is S because the priority groups are in cis position. Here also the priority groups of the double bond are in cis position. Hence this both double bond is ZZ. This is the diene is ZZ configuration, and here we can see this is E and this is Z, and here it is E and this is C. And we can see that the reactivity increases when it comes to the EE alkenes. So here the diene, we can conclude that for the diene to be a part in the Diels-Alder reaction, it can be acyclic or cyclic. It should possess electron-rich double bond, and it should have a cis conformation for the proper orbital overlapping with the diene of phi. And also to increase the diene reactivity, we should substitute the diene with some electron releasing group, especially E alkenes. Next, we can see what are the characteristic features of a diene. What should be the characteristic feature of the dienophile to be a part of the Diels-Alder reaction? If the diene is electron rich, dienophile should be electron poor alkene for the Diels-Alder reaction. Dienophile should be electron poor, so that to make the double bond of the dienophile to be electron poor, it should be substituted with some electron withdrawing groups. Here we can see some electron withdrawing groups here, that is carbonyl compounds, then cyanide ion substitution with the cyanoalkenes, and here we can see some ester group and a malic anhydride. This is quinone structure. These all are dienophiles. These all possess double bond, but it is substituted with some electron withdrawing groups. So these the double bond of this dienophile is electron poor. So these all can easily take part in Diels-Alder reaction. So here it is said that conjugated carbonyl compound. This is a conjugated carbonyl compound because the double bond is in conjugation with this carbonyl compound. That means the double bond could shift here, and then this double bond shifts to here. So this is a conjugated carbonyl compound. Then conjugated nitro compound, a nitriles. Here it is given a nitriles, sulfones, aryl alkenes, vinyl ethers, esters, haloalkenes, and dienes. These are another example for the dienophile with a double bond having very poor electron density due to the substitute. This is example for the sulfone substituted dienophile and all. Here we can see if you are taking an unsubstituted diene and an unsubstituted dienophile, the reaction will be with poor yield. But if we substitute this diene with any other electron releasing group to make it electron rich, and if we substitute this dienophile with any electron withdrawing group to make it more electron deficient, then the Diels-Alder reaction takes place readily with a high yield of the product. So these are the general characteristic features that a diene and a dienophile should possess while in the Diels-Alder reaction. Then we can see how to identify a Diels-Alder product. If a reaction is given to us and we have to identify what type of this reaction is this, whether this is a Diels-Alder product, we have to check for some features. Like if this is the product which is given to us, first we have to look whether there is a double bond to the ring. And second, we have to look whether there is a conjugated group outside the ring and if it is opposite to this double bond. Third, is there any formation for the six-membered ring? Is there any six-membered ring? These are the key important features that we should identify for a Diels Alder product. So, a double bond in the ring plus a six-membered ring plus a conjugating group outside the ring opposite to the double bond. These three features cumulatively identifies a Diels Alder product. We can see some examples for the Diels Alder reaction. Here we can see a butadiene reacting with a conjugated aldehyde. This is a conjugated aldehyde and this dienophile is electron poor due to the presence of conjugation with this carbonyl component of aldehyde group, carbonyl group of the aldehyde group, and here it reacts with a substituted diene. This is electron rich and this is electron deficient, and easily we get this product by the shifting of electrons. And this is the another Diels Alder reaction. Here cyclopentadiene, and we can see this is of a cis conformation, and here we can say dienophile substituted with the best reductant with direct group nitro group, and we can see the product here. We have to note that the cyclopentadiene has 5 carbon atoms, but only these 4 carbon atoms takes part in the reaction. 4 carbon atoms take part in the reaction. 1, 2, 3 and 4. Hence 4 plus 2. 1 and 2 carbon atom, 4 plus 2 cycle addition reaction. And this carbon atom is seen intact here without any reaction. Only the 4 carbon atom should take taking part in the reaction to get this product. And here we have another example, and from this example we can say that Diels Alder reaction can be used to make more complex product. That means it find its role potential in making medicines, the medicinal chemistry. So in the medicinal chemistry field, and here we can see as 2 starting material, and here this diene is in a cis conformation, and this is a dienophile with the in the quinone structure with the 2 carbonyl compounds conjugated with this double bond to make it more electrophilic. That means electron loving, which means this is electron deficient and it undergoes Diels Alder reaction to get this complex product. So Diels Alder reaction can be used to produce more complex product. The other application of Diels Alder reaction comes with the trapping of benzene intermediate via 4+2 Diels Alder reaction. Here we can see benzene intermediate, which is formed from the most common reaction anthracyclic acid with alkyl nitrate. We get benzene. We know that benzene is a reactive intermediate. It is very unstable. It is very reactive. So to trap this benzene intermediate, we have used anthracene via Diels Alder reaction. Here in the anthracene structure, the double bond of the middle ring is having more electron density. So this acts as a diene, and we know that this is in S-cis conformation. This diene reacts with the electrophilic benzene. This benzene is electrophilic, that means it is electron deficient. Benzene intermediate is electrophilic, that is it is electron deficient, and hence the alkane part of this benzene could act as a dienophile, and it reacts with the electron rich double bond of this anthracene, and we get a 4+2 cycloaddition reaction to get this product. Here we can see the orbital interaction of this benzene with the anthracene. It aids in a suprafacial interaction to get easily the 4+2 cycloadded product. This is another example for the cycloaddition reaction, trapping of oxyallyl cation via 4 plus 3 cycloaddition reaction. Here we can see an oxyallyl cation. This oxyallyl cation, this is the allyl structure C H2 double bond C CH 2 plus. This is an allyl cation with the oxy substitution. So oxyallyl cation. This is formed from a dihaloketone. From a dihaloketone here, when it reacts with the zinc, the zinc donates its electron to the oxygen, and thereby the electron zinc donates its electron to the oxygen, thereby the electron shifts to here and Br get eliminated as Br minus and we get a double bond, and this Br also get eliminated as Br minus, thereby forming a positive carbon carbocation center, and this is an allyl cation with the oxy substitution. So this is oxyallyl cation, and this is also a reactive intermediate short-lived species, and to trap this oxyallyl cation, we are making this oxyallyl cation to get reacted with the butadiene, and this undergo a 4 plus 3 cycloaddition. Why it became 4 plus 3 means in the part of oxyallyl cation, we can see a 3 carbon centers taking part in the reaction. 1, 2 and 3, and in the other there is 4, so it is 4 plus 3 cycloaddition reaction, and we get this product. This is another example for the Diels-Alder reaction when it comes for the industrial application. Here we use a hexachlorocyclopentadiene. When it reacts with the maleic anhydride, we get a flame retardant. This is also a 4 plus 2 cycloaddition reaction, since it involves only 4 carbon atom in the part of diene and only 2 carbon atom in the part of dienophile, and we get a flame retardant. Another industrial application of Diels-Alder reaction comes with the synthesis of agricultural fungicide captan with the reactants diene and maleic anhydride. So butadiene and maleic anhydride to get directly the Diels-Alder reaction. Then on further treating with ammonia, we get captan. These are all about the general interaction for the Diels-Alder reaction. In the further videos, we can discuss about the regioselectivity, stereoselectivity, and some further more explanation of Diels-Alder reaction. Thank you. Hope you all enjoyed the video. Thank you.